Hi everyone. So in this video we are going to study about Cascode. First we will study about Cascode current source, then we will study about Cascode amplifier, and then we will see Cascode amplifier with Cascode current source. So this we are going to see, but let's study one by one, not directly jumping onto the topic. So first we will study current source. So what is a current source? You might have studied in basic network analysis. So what is the current source? Current source provide a constant current irrespective of the voltage across it. So that is an ideal current source. But every current source has some internal resistance. So let's just assume this is our current source which is having some internal resistance that I am calling is R out. R out. So current source is having its resistance. This could be anything. This supply could be VDD. So current source is having its resistance. Now this is the load. This is the load resistance. RL is the load. So in load, how much current is going? Let's assume this is some I dash current. So one thing I certainly know that I dash is less than I. Say yes or no. I dash will certainly be less than I. Why so? Because this R out will eat up some current. This R out will eat up some current. Right? Tell me one thing. If R out is infinity, if R out is tending to infinity, or if R out is infinity, then what will happen? This I dash will be equals to nearly equals to I. Or I can say this I dash will also be tending to I. Right? So more the R out, better the current source. More the R out, better the current source. If R out is high, that means you will have more current in the load. Your target is to get the current in the load, right? Not in this R out. You are collecting your final output here. You are collecting your final current here. So your target is to get the more current in the load. So more R out, better current source, right? So as much R out you are having, better the current source you will be having. So if you are making a current source, you should make sure that it has maximum output impedance. If you are making a current source from a device, what devices we have studied? We have studied diode, we have studied MOSFET. Now we are going to make a current source using some device. What that device will be, that I will tell you. So we have to make sure that its output impedance is high. That's it. So what we have studied? We have studied MOSFET. So we can make the current source using MOSFET. So making a current source from MOS. This is the characteristics of MOS, right? ID versus VDS. In which region it should be working as a current source? Tell me. What is the property of current source? It should provide a constant current. Is the current constant here? No. If VDS changes, the current is changing, current is increasing. Here the current is nearly constant, right? In this region the current is nearly constant. That means when you are using the MOS as a current source, it should be biased in saturation region. So what is the point? For using MOS as a current source, it should be biased in saturation region. This is the saturation region. Now I have made these characteristics for three different MOS. For three different MOS. For one of the MOS, this is the scene. In saturation region, it is going like this. For the next MOS, it is going like this. And for the next MOS, it is going like this. So which one is the best? Tell me. Which MOS is the best current source? Let's call this MOS as M1, this MOS as M2, and this MOS as M3. So tell me which MOS is the best current source? Which MOS will act as best current source? M1. Why so? Because it has the highest output impedance. R01 is greater than R02 is greater than R03. R01 is nearly infinity because this slope is 0. If del ID by del VDS is 0, that means what is R out? 1 upon del ID by del VDS. So that would be nearly infinity. So ID by VDS, that is nearly equals to 0. So R out is the highest. So in M1, R out is highest. M2, R out is lower than R01. And in M3, R out is lower than R01 and R02. So this is the best R out. That means highest R out. That means this is the best current source. Best current source. So M1 being the best current source. So what did you understand? If you need a MOSFET as a current source, you need to bias it in saturation region. Also, better the R out, better the current source. More the R out, better the current source. If you are having more R out, that means your current source would be better. So here M1 is the best current source. This is what we have understood till now. So if we are making a current source, you can use a MOS. So this is what we are going to write. You are making a current source, you can use a MOS. What is this VN? VN is a node. And this is a ground. So you are making a current source using MOS. So this is a VN. Between VN and ground, we need a current source. So I will use a MOSFET. This potential will be VN. This potential will be some VGG. We can give a supply from our own side. It would be some VGG, and this is the ground. What is the output impedance? Small signal output impedance looking from here. Tell me. This VGG will be grounded. VGS is gone. So only it sees R0. Say yes or no. What did I say? Small signal output impedance we are saying. So this will be shorted. So VGS will be gone. This MOS will be replaced with open circuit, but it is having some R0 here. So final output impedance is R0. Say yes or no, right? Now, why did I use NMOS? Why did not I use PMOS? Let's check what if I use a PMOS. So this will be my VN. I will be using a PMOS. This will be some supply VGG, right? If I use a PMOS, tell me what will be the impedance looking from here. If I use a PMOS from VN to ground, if I use a PMOS, what will be the impedance looking from here? What will happen? This VGG will be shorted. Then from VN to ground, you see 1 by GM. From VN to ground, you see R0. Here VSG is not gone. Here VSG was gone. So complete MOS was replaced with open circuit and R0 only you could see. But here what is the output impedance? 1 by GM parallel with R0, which is not greater than R0. So if you are getting a current out of a node, if you need a current source where the current is getting out of the node and going into the ground, you will use a NMOS, not PMOS. Because if you are using PMOS, then if you look from here, your impedance is 1 by GM parallel with R0, not R0. And you need very high impedance, not 1 by GM parallel with R0. 1 by GM parallel with R0 is nearly equals to 1 by GM only, which is not that high. Let's just assume 1 by GM is some 100 ohm and R0 will be some 100 mega ohm. So what will be the equivalent impedance? That would be nearly 100 ohm only, right? So this is not what you want. You want a higher output impedance. Here you are getting the output impedance as R0 only, right? So you don't use a PMOS. So if you are going from a node to ground, that means you will use NMOS, not PMOS. Now, if you are going from VDD to VN, then we will use PMOS. So this is your VDD. Yeah, one more thing. It's not that this will not be working as a current source. Yeah, it will work as a current source. And in some circuit, you will see they use PMOS as well. But this is desirable. What I am saying, it's not that it will not work as a current source. It will also work as a current source, but very weak current source because it is having 1 by GM parallel with R0. So it's not that you cannot use it. You can certainly use it. But generally, from VN to ground, you use NMOS, and from VDD to VN, you use PMOS. You don't need to mug it up. You don't need to mug it up. When you draw a circuit, it will directly come to you. Okay, I cannot use PMOS here because this is the impedance. I cannot use NMOS here. This is the impedance. So no need to mug it up. And once we see further circuit, it will come to you all, by its own. So no need to mug it up. This VGG supply we can give, and this is the VN. So you will see the impedance from a node, not from here, because VDD will be shorted. If you do the small signal analysis, this VDD will be shorted, this VGG will be shorted. So this will be shorted, this will also be shorted. You need to see the impedance from here. So VSG is gone. That means this MOS will be replaced with open circuit. So from VN to ground, you only see R0. That's it. VDD is gone, VGG is gone. So VSG is gone. If VSG is gone, that means zero current. So MOS is replaced with open circuit. So from VN to ground, you see only R0. So what is the impedance you see? That is R out. From here, the impedance is R out. What if I had used NMOS? So what I would have done? This is my VDD. I would have used the NMOS. This would have been my VN. And this is VGG, whatever it is. So what would be the impedance looking from here? That would be from VN to ground, I see 1 by GM. From VN to ground, I see parallel with R0. So impedance would have been 1 by GM parallel with R0, and this is not desirable for me. So you have made a current source using MOS. So what I will write, from node to ground, if you are going from node to ground, that means you will use NMOS. If you are going from supply to node, you will use PMOS. If you are starting from node, that means NMOS. Node NMOS. If I am starting from a node and I am going towards ground, I will use NMOS. If I am starting from supply to node, that means I will use PMOS. Where the supply will be? Supply will be at top, because we have seen a lot of circuits where always VDD is here. VDD will be at top. Supply will be at top, right? So supply will be at the top. So if you are going from top to a node, you will use PMOS. How you can remember? P, top. Last word is P. So if you are going from top to some node, that means you are going to use PMOS. Supply equals to top, top means P. Last word is P. So I am using PMOS. That's how you can remember, just a method to remember. Otherwise, you will certainly be habitual of making the current source by using NMOS and PMOS. Once we end the lecture, at the end of the lecture, you will be very comfortable with making the current source and everything. So this is what we have made. Now the R out we are getting is R0, right? The R out we are getting is R0. What if I get a higher output? I will try to make a higher output. I want a higher output impedance. My output impedance is R0. I want a higher output impedance. So what do I need? What if I need a higher output impedance? So try thinking of the circuit. What that circuit will be? Tell me. Do you remember any formula of impedance? Any formula? Do you remember any formula of impedance? Yeah, we remember. R0 plus RS plus GM R0 RS. Is that impedance higher than R0? Yeah. We remember this formula. And what is that formula? If you are going from drain to source and your gate is common, if you are going from drain to source and your gate is common, that means this will be the impedance you will be getting. So simply make that circuit and you can use that as a current source. That's it. If you are going from drain to source, that means from here, from this node, you will see R out. That would be R0 plus RS plus GM R0 RS, which will nearly be equals to GM R0 RS. Say yes or no. So if you are going from a node to ground, that means you are going to use NMOS, node to ground. Now if you are going from a node to, if you are going from a supply to node, that means you have to use a PMOS. So basically this circuit will be replaced by something like this. A current source, a DC current source from a node to ground, and that is having an output impedance, that is this R out. which is nearly equals to GM R naught RS. Here, what do you see? What is the impedance here? You are going from drain to source. If you are going from drain to source, that means you need only one step behind. So it would be R naught plus RS plus GM R naught RS, which will nearly be equals to GM R naught RS only. So what do you see here? From VDD to a particular node, that is Vn. This is your VDD to a particular node, and in between you are having a resistance. That resistance is GM R naught RS. So this is my current source. Okay, so this is what I have made. Now what if this is my output impedance? What is my output impedance? Nearly that is equals to GM R naught RS. This is a very high value. Now this RS is depending on you, right? You can connect this R naught. Sorry, you can connect this RS. This RS is depending on you. What if I make it very high? RS should be very high. How I can make it very high? Tell me. RS is the impedance looking from here, right? RS is the impedance looking from here. So I need to make an impedance which is very high if I see from this output. How can I make it? This, and this. VB. What will be the impedance from here? That will be R naught. Right? Now don't say, sir, connect one more RS here. So impedance will be more higher. But we don't want to use this much of elements. Okay, we don't. If I use another in place of RS, if I use another this circuitry, my impedance will be more higher. But we don't want to use like that. If I keep on adding up, my impedance will be very higher. But we don't want to use that much of circuitry. Minimum circuitry also we need to use. If we use that much of element, then first thing is that power consumption will be more, and second thing, the device will be costly. The chip will be costly. But you don't want to make or design a costly chip. So simply you are replacing your RS with this MOS. That's it. So from here, what will be the impedance? If you look from here, what will be the impedance? This VBB will be shorted. So this VGS is gone. So only impedance is R naught. So you have replaced your RS with R naught. Say yes or no. Right? So this is what we are going to do. We are keeping this as it is. This also as it is. We will just replace this RS. We will replace this RS by using a MOS. Right? And this gives rise to our cascode current source. So what we are going to make from VDD to ground first we are going to make. This is our VDD. From VDD to ground we are going to make a current source. Sorry, not from VDD to ground. From a node to ground. Sorry, not VDD to ground. From a node to ground. This will be our some DC supply, bias supply we are saying. So VB1 I am calling it. This is my bias supply. It will be having some R naught here. Let's just forget about R naught. Then we are making this RS by using a MOS only. So this is the current source. So what will be the impedance looking from here? R out. That would be GM R naught. Let's call this one as M1, this one as M2. So the impedance would be R naught 1 plus R naught 2 plus GM R naught 1 R naught 2. That's why I told you to remember this formula, because here you are directly writing it. You are directly writing the impedance, which is nearly equals to GM R naught 1 and R naught 2. And this is known as cascode current source. This is not cascode amplifier. This is cascode current source. From Vn to ground. From Vn to ground, you have made a current source. That is cascode current source. Are you getting this point? How did I write the impedance? This VB2 will be shorted. So this M2 will be replaced with the R naught 2 only. We have already seen this configuration for output impedance. But at that time I did not tell you what is this. Now here I am telling you this is Cascode current source. And what about this M1? This M1 will be made something like this. You just have mugged up one formula R0 plus RS plus GM R0 RS. By using that only you are writing the impedance. From here you are writing the impedance, that would be R01 plus R02 plus GM R01 into R02. That's it. Well and good. Directly you are writing the formula. So this is using NMOS. Now task for you is make the current source from VDD to some supply. Sorry, from supply to some node. From VDD to VN. Make the current source using PMOS. Because if you are going from top to some node, you have to use PMOS. Top to some node. So this was the first one. This is the Cascode current source. Now you are going from top to some node. This is your VDD. Both bias we can give VB1 and VB2. And this is the node VN. And from here you need to see the output impedance. Tell me what will be the output impedance. What will happen to this? Let's call this as M2, this as M1. What will happen to M2? VDD will be shorted, VB will be shorted. So VSG is gone. So M2 will be replaced with R02. Now M1 and in D generation there is R02. D generation means this will be the circuit. VB2 will also be shorted. So this will be R02. So doesn't it look like common source amplifier with degeneration? Isn't it common source amplifier with degeneration? Common source is common source amplifier with degeneration. So the resistance would be GM R01 R02. You are going from drain to source, that means you need only one step, GM R01 R02. That's it. So our output impedance is R01 plus R02 plus GM R01 R02, which is nearly equals to GM R01 and R02. So this we have studied. We have studied the Cascode current source. So this is the Cascode current source, right, which is having a very higher output impedance. So this is a great current source which we have made using MOS circuit only. So in the interviews, sometimes they can ask you make a Cascode current source, and even in the gate examination, they can make 4 options, and they can ask you to choose which is a Cascode current source. They can make it using NMOS as well. They can make it using PMOS as well. So these kind of questions can be asked. So this is the Cascode current source. Well and good. Now let's write down the summary. So if you are going from VDD to a node, if you are going from top to a node, that means you will use PMOS. So what are the other ways? First way we saw by using a simple MOSFET. So what was the output impedance here? The output impedance was simply R0. This was your VDD and this was your VN. So the impedance here was R0 only. But then we came to our Cascode current source. So in Cascode current source, what did we do? Or before going to the Cascode current source, what we made? This was the first one. Then we made RS here. This was the RS we were already having, and then we were having a MOS. So if you look from here, the impedance would be, this is VDD. So the impedance would be GM nearly the impedance would be GM R0 RS. Right? This is the second question. What about the third? Not the second question, sorry. Second method. What about the third? We made RS using MOS only. So we made RS using MOS only. This is VB1, VB2. This is your VN. Your R out would be, let's call this one as, what did I call? M2. This one as M2, this one as M1. Here also GM also we need to write. This is GM1, GM1, GM of this, GM1, GM1, GM1. So R out would be GM1, R01. This will be replaced with R02. Right? So these were the three methods we studied, and this one is given a name, that is Cascode current source. Right? Now we will make the same for from VN to ground, from a particular node to ground. So what was the first one? We simply used a, this is the way, we simply used a NMOS. This is the first one. What about the second? VN, what was the output impedance here? That was R0 only. Impedance from here is GM R0 RS. Right? So this was the second one. In the third one, we made the RS using MOS only. So what will be the impedance from here? That would be GM1 R01 R02. So till now, whatever that we have studied, that is covered in the last two slides only. So if you just revise this last two slides, you will be able to understand everything. And this is not the complete one. This is the approximate R out. GM1 R01 R02. So in the last two slides, we have seen everything. So our target was to make a cascode current source. Now we have made the current source. What we will do with that? So let's understand by a question. So you have to design a common source amplifier using cascode current source in the load. So in the load you are going to use cascode current source, and then you need to write down the small signal voltage gain. Small signal gain means small signal voltage gain, and you need to make the common source amplifier using both PMOS and NMOS. So let's make CS amplifier using CS amplifier, common source amplifier using NMOS with the current source in load. With current source in load. So what is our common source amplifier? Our input is applied at what? Gate. This is the input that is applied at gate. And where do we collect the output? At drain. We collect the output at drain. So in the output you need a current source. Load means in the output. In the output you need a current source. I will make it better. So VDD, in the output I need a current source. And here I am collecting my output. So at the load we used to connect RD, but here we are connecting a current source. So this is the amplifier we have designed. Well and good. Now they are saying that this current source should be made using cascode. So this current source should be cascode current source. Yes or no? So we have to make a cascode current source. So how will you make a cascode current source? You are going from VDD to a particular node. You are not going to ground. You are going to a particular node and you are starting from top. So from top to a particular node, you will use PMOS. So you have to use PMOS. So now this is VDD. I need to use cascode current source. This will be a particular VB1, VB2. Let's call this one as M1, this one as M2, and this one as M3. And here you are collecting your output. So this is this particular configuration that you see here. This is a cascode current source. What is this complete configuration? What is this complete figure? That is common source amplifier with cascode current source in load. Cascode current source in load. That's it. So don't confuse it with cascode amplifier. This is not cascode amplifier. This is common source amplifier with cascode current source in load. Say yes or no. Right? So in the examination, they can give you this particular circuit and they can ask you what kind of amplifier it is. Then people will say this is cascode amplifier. Wrong. This is common source amplifier with cascode current source in the load. What will be its gain? Tell me. You need to replace this much impedance with this much of circuit with some impedance. What will be that impedance? We have seen exactly the same circuit in the previous videos. In the assignment, we have seen exactly the same. So what will happen to M3? M3 will be replaced with the R03. And from here, what is the resistance you see? Nearly it is equals to GM2, R02, R03. Right? And from here I see nearly equals to R01. So what will be my gain? Gain will be minus GM1 in parallel to this resistance. So V0 to ground IC R01. From V0 to ground IC R01. From V0 to ground IC, this is R03 and this is some MOS. So this impedance is GM2 R02 R03. So from V0 to ground IC R01 parallel with GM2 R0 to R03. So R01 parallel with GM2 R02 R03. So this is the impedance this is the gain that I am getting. This is the approximate gain because the impedance that we have that is approximated. This impedance is approximated. This is not the exact impedance. This is approximated impedance. Which one is the approximated? Here this R01 is not approximated. This is exact. R01 is exact. But this is approximated. Exact is R02 plus R03 plus GM2 R02 R03. Right? Well and good. Okay. So this we have made using NMOS. Now we have to make using PMOS. Current source should be in the load. Current source should be in the load. So what we are going to make now? Common source amplifier using PMOS with current source in load. Current source in load. So there should be common source amplifier. Common source amplifier. Where do you collect your output? At drain. This is the output. In the load, there should be current source. That's it. Did you understand it? Common source amplifier is that, and you are collecting your output at drain. So in the load, there should be current source. This is the current source we are talking about, right? Now you have to make a current source that should be using cascode configuration. So this should be cascode current source. How you can make it? You are going from a node to ground. node to ground. Node means NMOS, so you will be using NMOS. So in the next page, I guess I will have to add a page. Now this is the common source amplifier. No need to do anything with that. This is VDD. Now the current source should be made using Cascode configuration, using NMOS. This is VB1, this is VB2, and here you are collecting the output. What is the impedance do you see from here? What is the impedance? That is, let's call this one as M1, this one as M2, and this one as M3. So what is the impedance do you see from here? That is R01. What is the impedance do you see from here? This will be replaced with R03. This MOS will be replaced with R03 because this VB2 is gone. This VB2 is gone, so R03 will be replaced. So this VB1 will be shorted. So the impedance would be GM2 R02 R03. GM2 R02 R03. Right? So what will be the gain? The gain would be from here. What will be the current going in? Did I use the negative sign in the previous gain? Yeah, there is negative sign. So what will be the current going in? This would be the current. GM1 V in. The current would be GM1 V in the upward direction, and that would be flowing through this impedance. That would give the negative gain. This is common source amplifier. We have already seen all these things. We have already seen. So what will be the gain? The gain would be minus GM1 into this impedance. That is R01 parallel with GM2 R02 R03. Say yes or no. Are you able to understand these points? So we have made common source amplifier with current source in load, and we have made the common source amplifier using both PMOS and NMOS. When we were making common source amplifier using NMOS, then the current source in load was using PMOS. This current source that we made, that was made using PMOS, but the amplifier was made using NMOS. So what is this particular configuration? This configuration is common source amplifier that is made using NMOS with cascode current source in load that is made using PMOS. Say yes or no. This common source amplifier is made using NMOS, and this current source is made using PMOS. What about this? This is the figure is common source amplifier with cascode current source in load. Current source in load. So this common source amplifier is made using PMOS, but the current source is made using NMOS. Are you able to connect all these things? I hope you are able to connect all the things. For you as a gate aspirant, what is important? You should be knowing which configuration is known what. This is common source amplifier. Okay. This is cascode current source. So you should be knowing this thing. The second thing is you need to write the gain. You should be able to write the gain. How you can write the gain? I have told you multiple methods. I have told you the GMR out method as well. So if you needed to write the gain using GMR out method, how would you write the gain? Output is shorted. Then the current flowing is GM1 V in. So that current would be flowing like this in upward direction, GM1 V in. So your I out would have been minus GM1 V in. So your GM would have been minus GM. And then output impedance, this is the output impedance. So output impedance also you could have written, right? So this is how you could have write the gain. So for a gate aspirant, it's important that you should be able to write the gain. Also, you should be knowing what configuration is known what. This configuration is known as common source amplifier with cascode current source in load, because in the examination they can ask you which one of the 4 option is that particular configuration. So I hope you are comfortable with all these things till now. In gate field, in gate industry, this is not even taught. Forget about explaining it. This is not even taught, because a lot of teachers and even the educators, even the student, I should not say it, but yeah, they are not that much of comfortable with these kind of topics. But here we are dealing it in very good manner. Slowly we are going. We started from one MOS. Now this is the configuration. Now we will make it more complex. Now what is the issue in this one? Tell me. What is the issue? You made this common source amplifier with using cascode current source. What is the gain you are getting? This is the gain you are getting. In the output impedance, what is the seen? R01 is parallel to GM2, R02, R03. Right? R01 is parallel to GM2, R02, R03. What will be the equivalent of this? This is very high, right? And this is not that much high. This is high, but this is very high. So what will be the equivalent? R01 only. So what will be the gain? The equivalent gain you are getting is minus GM1 R01. Is that high? Is that pretty high? No, this is not that much high, right? Your target would be, now my target is to get a high gain. I have made a current source which is having higher output impedance. So this current source is good. This current source is good. But when I check the gain, it is nearly minus GM1 R01, which is not that much high. But I need a higher gain. What I would do? I need a higher gain than this. And in the next one, here also the gain is nearly minus GM1 R01 only. Now I need a higher gain. So what I would do? I use Cascode amplifier. I will use Cascode amplifier. So we need to build a higher gain amplifier. So what we can do? This is our gain, GM into R out. So keeping GM constant, increase R out. The design we made in the previous problem. So what is our R out in the previous design? That is R01 parallel with GM2, R02, R03. So this is the R out. You need to increase this R out. Increase R out. So you need to increase this R out. So in the previous problem that we made, this was the R out. So keeping the GM constant, I need to increase the output impedance. How I can increase the output impedance? There is a current source in the load. There is this current source in the load. So this is actually very high, right? This impedance is actually very high. The problem is this is low. I need to increase this impedance. What can I do? The first thing that can come to your mind is that, sir, degenerate it. If I degenerate it, sir, degenerate it. Okay. So, sir, if you degenerate it, what will be the impedance here? Let's call this one as M1, and this will be shorted, whatever it is, because here you are applying V in. So what will be the impedance looking upside? That would be, let's call this as RS. That would be GM1 R01 RS. You are going from drain to source, only you need one step. So GM1 R01 RS. Sir, you have increased your output impedance, but your GM is changed. I told you, keeping the GM constant, your capital GM would be changed. How it will be changed? Where you would apply the input? You would apply the input here. Right? Now the current is GMV in. Tell me, the current is GMV in. In all the previous questions, your current here was GMV in. Right? Now the current is not GMV in, because this end is not grounded. This end is connected to RS. So this is not what we can do. Right? So what we will do? We will make this RS using MOS only. But we will apply the input here. This is the different thing we are going to do. That's why it is known as cascode amplifier. If I do this, what this will be? This will be common source amplifier with degeneration and cascode current source in load. Say yes or no. What this configuration would be called? What this configuration would be called? And there will be this current source also in the load. So common source amplifier with degeneration and cascode current source in load. But now what I am going to do, I am going to apply my V in here in the RS part. In the RS part, I am going to apply my V in. So what that will do? My current here would be GM V in. So my GM will be constant. And this configuration is known as cascode amplifier. Are you getting this point? So let's just write it down. So I have given you the idea how did I thought of it. But that is not that much of important because no one is going to ask you how did you thought of it. Actually we did not thought of it. The engineers thought. ठीक है, जो लोग बना गए उन्होंने सोचा ऐसा, हम तो बस देख रहे हैं. बट what is the criteria? If you keep on thinking the things like that, you will end up designing a very good circuit in the future when you go into the industry. So I am developing that thing in you so that you get comfortable with thinking as well. It's not that you just need to write the gain, etc. You should be thinking how we are getting this much of high gain. So now I will come up with cascode amplifier. Okay, so this is my cascode amplifier. So I am coming up with cascode amplifier. So I told you one thing, I will make something like degeneration only. Okay, so let's make it using NMOS. We will make the cascode amplifier using NMOS. So in my NMOS, what do happen? There will be a current source that would be coming here. This would be some ID. This would be your output. Where will I apply my input? Here I will apply my input. And this will be some bias. Are you getting this point? So what will be the output impedance here? Since this is a constant current source, the output impedance is infinity. So what is the output impedance here? Looking here, let's call this one as M1, this one as M2. So what is the output impedance? Tell me. Approximate impedance you need to tell me. That would be, this will be shorted, this will also be shorted. We are writing output impedance. You are writing output impedance. So if you are writing the output impedance, this will be shorted. This will also be shorted. So if V in is shorted, then this MOS M1 will be replaced with R01. And what will be the scene then? This is M2. This is replaced with R01. This will be shorted. And this is R02. So from here, what do you see? That is GM2, R02, R01. Right? You are going from drain to source. You need only one step. GM2, R02, R01. So the impedance would be nearly GM2, R02, R01. Right? And what will be capital GM? For capital GM, what you will do? You will short circuit the output. So what is the current flowing here? That is GMV in. And you need to find out this I out current. So I out is equals to GMV in minus GMV in. I out is equals to, the same current will be flowing. That would be minus GM1 V in. It should be approximated. Why so? Because I am considering that R01 and R02 are very high. If I am considering R01 and R02 are very high, then only this GMV in current would be equals to I out. We have seen this in assignment. In previous assignment, we have seen this. If I am considering R01 and R02 are very high, then only this GMV in current will be flowing directly in the output. Otherwise, the R02 and R01 can eat up some current. But this is not happening here, right? So my capital GM is approximately equals to minus GM1. So what is my gain now? That is, here I can write down my gain. That is GM R out. So it would be minus GM1, GM2, R02, R01. So this is the gain I am getting, which is very high. Although we have seen this gain in previous videos in the assignment, but there I did not tell you which configuration is known what. So here I am telling you this particular configuration. This particular configuration is known as Cascode amplifier. This is what? Cascode amplifier with the current source in load. Cascode amplifier with current source in load. Now we will make the same thing using what? Using PMOS. So in PMOS, common source amplifier. Common source amplifier. This is the common source amplifier. This supply. Where will I apply my input? Here I will apply my input, not here. If I apply my input here, this will become R02 or whatever it is. We will call this one as M1, this one as M2. So if I apply my V in here, what will become? What will happen? This will become R01. So my GM would be changed. I do not want my GM to be changed. So this is M1, this is M2. Here I will give DC supply VB1, and here there will be current source. And this is where I am collecting my output. I am collecting my output at drain. Right? So this particular configuration is Cascode this particular configuration is Cascode amplifier, right? And what will be the gain? Tell me. The gain would be this only. You can write down the gain on your own. Say yes or no. What will be GM value? The current is GMV in. GM value would be minus GM1. What will be R out? Minus GM1. What will be R out? From here to ground, this is the DC current source. So it will be infinity impedance. And now from here to ground, what is the impedance do you see? What is the impedance do you see? This will be shorted, so this will become R01. So GM2, R02, R01. That's it. GM2, R02. This will become GM2, R02 and R01 then. GM2, R02, R01. That's it. That's the gain we are getting. So this is Cascode amplifier using NMOS. This is Cascode amplifier using PMOS. Now what you can do? You can make this current source using Cascode current source. So now we are going to make Cascode amplifier with Cascode current source in load. Cascode amplifier with Cascode current source in the load. So that will be our last circuitry. This should be Cascode amplifier with Cascode current source in load. So this one we are going to make, this current source we are going to make using the Cascode configuration. So where we are going? We are going from supply from top to some node. That means we need to use PMOS. So Cascode amplifier with Cascode current source in load. So we are making a current source using PMOS. That will go from supply to some particular node. And then we are having a Cascode amplifier. This I can call VB1. This will be VB2. This will be VB3. And here is the output. Say yes or no. Are you agreeing to this point? This is our circuit, and what is this configuration known as? This is a Cascode current source. This is what? This particular configuration is Cascode current source. And what is this? This is Cascode amplifier. Writing कितनी सही होगी ना मेरी? So this is Cascode amplifier. This is Cascode current source. Say yes or no. Are you agreeing to my point? What will be your approximated GM here? Approximated GM. Where is the input? Here is the input. The current would be GMV in. You are shorting the output, right? So approximately it will be GM1. Let's call this one as M1, this one as M2, this one as M3, and this one as M4. So approximately the GM would be GM1 minus GM1. Why it is minus GM1? Output will be shorted. This current you need to write I out, and the current here is GM1 V in. Why approximately? Because there is R01 and R02 as well, which can eat up some current, but we will assume that R01 and R02 are very high, so it is not eating up some current. So GM1 V in would be flowing through output only. So I out would be minus GM1 V in. So capital GM would be minus GM1 only. Well and good. Okay. So GM is GM1. What about R out? Write down the R out on your own. Tell me what will be the R out. See the impedance here. VB3 is shorted, VB2 is shorted. If VB3 is shorted, this M4 will be replaced with R04. VDD is ground. VB3 is shorted, VDD is shorted. So M4 is gone, only R04 will be there because VSG is gone. And what about this? This is the scene, this VB3 is shorted. So what is the impedance from here? GM3, R03, R04. Say yes or no. GM3, R03, R04. The same thing is happening downward. This is shorted, right? This M1 V in is shorted, so VGS is gone. If V in is shorted, VGS is gone. So M1 will be replaced with R01. So what is the impedance downward? This is our V0. So what is the impedance downward? This is M2. So GM2, R02, R01. So what will be the total impedance? From V0 to ground, you see this. From V0 to ground, you see this. The impedance would be GM2. This is R02. GM2, R02, R01 parallel with GM3, R03, R04. Say yes or no. Well and good. Actually, we can keep it here like this. So yeah, this is M3. This is M2. What is our R out? R out. R out we can write down here. This is also approximated because exact one is the bigger formula, that is R03 plus R04 plus GM R03 R04. So which is we are not writing. So this is the R out we are getting. GM3 R03 R04 parallel with GM2 R02 R01. So this is the GM R out value you are getting. So what will be the gain? So this is your gain minus GM approximated, again approximated, minus GM1 GM3 R03 R04 in parallel to GM2 R02 R01. That's it. This is the small signal voltage gain. And what is this figure? This figure was, okay, it is written cascode amplifier with cascode current source in load. So this was the cascode current source and this was the cascode amplifier. This was the cascode amplifier. This was the cascode current source. Now you made the cascode amplifier using NMOS. Now you have to make the cascode amplifier using PMOS. And in the load you will use what? Cascode current source. That will be made using NMOS. Are you getting confused? Look, this is cascode amplifier made using PMOS. If you are listening very carefully, you will not get confused. That is my guarantee. This is cascode amplifier made using PMOS. Cascode amplifier using PMOS. And this is cascode amplifier made using NMOS. Now we are going to make this configuration. Now this current source will be made using cascode configuration. So if you are going from a node to ground, node N, that means you will be using NMOS. So for making this current source, you need to use NMOS. Now this will be as it is, this will be made as it is, and this you need to make using NMOS, and that we have previously made. We have made the current source using NMOS, where here it is. So this configuration will be used. Right? Cascode amplifier using So this I am making, that is cascode amplifier, and current source will be made later on. This is the cascode amplifier we are making. Where will we apply the input? We will apply the input this side. If I apply the input here, this will be made RS. That will change my GM. How it will change, that we will see. This is my VB1. Now we are making the current source. So this is our cascode current source. This is VB2, VB3. If you take interest, this will be very interesting. This complete analog electronics very interesting. If you take interest and study it in that much of depth. In the examination, you will solve the problems in seconds. And you will say, sir, analog electronics came tougher, but we solved it very quickly. So we are getting a very good rank. Believe me, if you study from PrepFusion, you will treat your examination very lightly. Yeah. So enough of self-praise. Let's write down the gain. But before writing down the gain, let's clarify what is what. M1, M2, M3, M4. This is cascode current source. And this is cascode amplifier. What will be GM? Capital GM. That would approximately be equals to minus GM1 only. What is R out? From here, what do you see? From here to here, what do you see? GM2 R02 R01, because this will be replaced with R01 only. So GM2 R02 R01. GM2 R02 R01 parallel with what will happen to this one? This will be replaced with R04. So that will be GM3 R03 R04. GM3 R03 R04. So what will be the gain? The gain will be minus GM1 GM2 R02 R01 in parallel to GM3 R03 R04. So this is the gain. Say yes or no, right? So this is the small signal gain. Now we will see what if I had applied this input here. So I will copy this structure. I can copy this structure. So I have written what if. Yeah, मिट जा भाई. Okay, बनाना ही पड़ेगा. So first let's make the current source. This was the current source. These were the DC bias. So this was the current source, VDD, and then this was the amplifier. Okay. So in the cascode amplifier, what we were doing, we were applying the input at this M1. This was M1, M2, M3, M4. Here we were collecting our output. So this was our bias, VB3, VB2, VB1. And here we were applying the input, right? This we were doing. But what if I apply my input here? I apply my input here, and this is the bias. What if I do this? Okay, the main thing to notice here is this. I have applied my input on M2 and this is my bias. What will happen to R out? R out will be same, because when you are calculating the R out, you short circuit the input as well. So R out will be same. This will be replaced with R01 only. So what will be R out? R out, if you look from here, that would be GM3 R out. From upward direction, GM3 R03 R04, right? And what about this? This M1 will be replaced with R01 only. M1 will be replaced with R01. So again here GM2 R02 R01. So this is unchanged. This is same as before. Same as before. But what about GM? That is the task. What about GM? So what you will do for GM? You will short circuit the output. अरे भाई ये क्या कर दिया मैंने? वापस बनाना पड़ेगा. Let me pause the video and make it again. Yeah, so this is how I will find my GM, right? I will short circuit the output. All the DC bias are also shorted. So this will be my I out. I just copied this circuit. The same circuit is there. This is M4. This is M3. This is M2. This is M1. So I just copied this circuit. I am writing my GM. So this V in will be there. All the other bias will be shorted. I need to find the relation between I out and V in. Right? This will be replaced with a particular impedance. That will be GM3 R03 R04. And this M1 will be replaced with the R01 because this is gone, so R01. And this is your V in. Your output is shorted. And this is the I out we are getting. Right? Will there be any current in this impedance R0, GM3, R03, R04? There will be no current here because this is also grounded, this is also grounded. So there is 0 ampere current here. Right? So in conclusion, how your circuit is looking like now for GM, for finding GM. This is your R01. This is your V in. Here, this is your M2. This is the output. This is my I out. How will you find GM now? You need to find the relation between I out and V in. So what you can do, you can assume a V here. So the current here would be GM V in minus V. GM V in minus V. So your I out is equals to negative of GM V in minus V. What also you can write down that my V by R01 is equals to negative of I out. Say yes or no? V by R01. This I out current is flowing this way. I out current is flowing this way. I am assuming what I am assuming that my R02 is very high. This is my GM2. I am assuming my R02 is very high. This R02 is not eating up any current. This is what I am assuming. Because if I take R02 in action, what will happen? This I out will not be equals to minus GM2 V in minus V. Because here there will be R02. So that will also eat up some current. So let's forget about that. We will write down the approximate formula. So I am assuming R02 is very high. So I out is flowing this way. So what will be your V? V will be minus I out R01. Say yes or no? V will be minus I out R01. Just put it here. So I out would be minus GM2 V in and V would be minus I out R01. ठीक है ये let's open it up. So I out is equals to minus GM2 V in plus GM2 R01. Is there something wrong in the calculation? GM2 V in minus V naught. Okay, I out. And this I out is flowing like this. So I out by R01 minus, put the sign there. Yeah, this will be plus. This I was thinking. This will be plus. So here GM2 V in minus GM2 R01 I out. So here I out by V in, that is equals to capital GM, that is equals to minus GM2 upon 1 plus GM2 R01. This will be your capital GM, right? So what will be your gain now? Gain. Now what is happening to GM? Previously what was your GM? Here your GM was GM1. Now your GM has reduced to this much of. Your GM has reduced. Minus GM2 divided by 1 plus GM2 R01. So your GM has reduced. GM is reduced. So your gain will also be reduced. That would be minus GM2 divided by 1 plus GM2 R01. And what was the output impedance? Output impedance was same. GM3 R03 R04 parallel with GM2 R02 R01. So this gain is reduced. Gain is lesser than, gain is reduced. Just I am writing reduced than what? Reduced than cascode amplifier. Reduced than cascode amplifier. So if it is not cascode amplifier, then what amplifier is it? Think about it and tell me. What is the name of this particular configuration? Tell me. If this is not cascode amplifier, then what is the name of this configuration? This is common source amplifier with degeneration that is having cascode current source in load. Say yes or no. This is common source amplifier with degeneration only. Are you getting my point? What is the gain of common source amplifier with degeneration? Minus GMRD upon 1 plus GMRS. Say yes or no. This is the GM for them, and this is the output impedance. What is the output impedance? This is the output impedance. What was the GM? Minus GM2 upon 1 plus GM2 R01. GM2, GM upon 1 plus GMRS. GM upon 1 plus GMRS. GM2 upon 1 plus GM2 R01. So this is the GM2 upon 1 plus GM2 R01, and this was the output impedance. Say yes or no. So this was common source amplifier with degeneration with cascode current source in the load. Right? So this is not our cascode amplifier. What is our cascode amplifier? This is the cascode amplifier. This is the cascode amplifier. And that was cascode amplifier with degeneration in the, that was common source amplifier with degeneration in the load. So I will write down one last thing, that is cascode amp versus common source amplifier with degeneration. Common source amp with degeneration, right? I will make a divider. Here I am writing cascode amp. Amplifier I will make using NMOS. Current source you can make using cascode. So I am not making current source here. This is VDD only. Here I am getting output. This is my cascode amp. And if it is cascode, where will I apply my input? Here I will apply my input. Right? This is VB. Right? And here I will be writing common source with degeneration amp using same NMOS. So what I will do, I will just copy this structure थोड़ा छोटा करना पड़ेगा. I will just copy this structure. I will just interchange this supply and here there will be this supply, here this will be VB. Let's call this one as M2, this one as M1, and here let's call this one as M1, this one as M2, or let's make the same name only, M2 and M1. So what will be the gain here? What will be the gain? The gain here would be minus GM1, and what is the R out? GM2 R0 2 R0 1. That will be the gain. What will be the gain here? That would be minus GM2 divided by 1 plus GM2 R0 1. Degeneration resistance is R0 1 into what is the output impedance? Output impedance is GM2 R0 2 R0 1. So that will be the gain here. The gain is reduced, right? And same cascode amplifier, cascode amp using PMOS. So this is VDD. This is our V out. Here I am giving the DC supply. If it is cascode, I will be using my V in here. I don't need to write the gain because the gain will be the same only as this. So here I am writing this is M1, this is M2, right? And if I am making common source with degeneration, okay, this was the third one, and this is the fourth one. So I am making common source with the degeneration amp using PMOS. What I need to do, I just need to copy this circuit. Just copy it. Okay, again I need to copy this circuit. Just copy it. Just interchange these. Let's call this as ID, this as ID. You can make this ID using cascode current source, right? So here you will be having your V in, here this will be your bias. I hope the complete lecture is clear to you, right? Everything that I have taught here, that is clear. What is cascode current source? What is cascode amplifier? Cascode amplifier with cascode current source. Common source amplifier with degeneration that looks like it is a cascode amplifier, but it is not cascode amplifier. This is cascode amplifier with degeneration. Sorry, this is common source amplifier with degeneration. So in the summary, what is the definition of cascode amplifier? We forgot to write definition of cascode amplifier. Just a simple note. What is cascode amplifier? So sometimes in the interviews, not in like VLSI interviews, but in some PSU interview, they can ask you what is a cascode amplifier. So cascode amplifier is common source amp in series with common gate amp. Say yes or no. This is your cascode. Common source in series with common gate. Common source in series with common gate. But the condition is common source should be either connected to the source. This is here, this is here. This is common source in series with common gate. Is this common source in series with common gate? Is this common source with series in common gate? No. This is common source with degeneration. Can you call this one as common source in series with common gate? Nah. This will be shorted, so this M1 will be replaced with RS. This is not an amplifier. M1 is not working as an amplifier. Only M2 is working as an amplifier. So here this is common source in series with common gate. The gate is common here. This is common source. Common source in series with common gate is known as cascode amplifier. Common source in series with common gate amp. So this is known as cascode amplifier. Sometimes in the written test or in 1 mark question they can ask this question. In the PSU interviews they can also ask this question. Well and good. One more thing I would like to tell you. One last thing. I will give you one intuition here. So here we found out the value of GM like this, minus GM2 upon 1 plus GM2 R 01. Okay, well and good. This is also a good method. I can find out the GM value by one more method. What do I know? This is V in. Here I am having V in. From gate to source or from source to gate, I know there is 1 by GM, right? 1 by GM2. And then there is this R01. And this is V in. This is V in. Here is 1 by GM2. Here there is R01. What will be the current here? V in by 1 by GM2 plus R01. So the current here, that is V in by 1 by GM2 plus R01. And this current is equals to minus I out. Say yes or no. From here also, from this equation also, you will get this GM only. GM2 will go ahead up. So GM2 by 1 plus GM2 R01. Are you agreeing to my point? One more intuition. By this also you can write down GM in one step only. This is V in 1 by GM2 R01. So the current downward is V in by 1 plus GM2 plus R01. That is equals to minus of I out. So I out by V in would be equals to GM2 upon 1 plus GM2 R01. Say yes or no. So this is my capital GM. That is minus GM2 upon 1 plus GM2 R01. Right? Well and good. Okay. This was just an intuition. You can write down in your notebook somewhere if you want to write down. Yeah. So sometimes in the interview, if you tell the things like that, interviewer will be impressed a lot of times from you, right? So if you study from this playlist, I'm pretty sure interviewer is going to be impressed from you. That is for sure. So let's meet in the next video. In the next video, we will be studying about current mirror circuit. So now we have made a current source, but that current source has some issues. What is that issue? First, we will see that we have made a current source, right? Cascode current source, but that is having some issue. What is that issue? We will address that, and then how do we eradicate it? We eradicate that using current mirror. So that we will study, and then we will see an assignment. In that assignment, we will study a lot of questions from current mirror circuit. Okay, thank you. Hi everyone. So in the previous video, we saw MOS as a current source. When we are using MOS in the saturation region, it acts as a current source with some output impedance, right? This is what we have seen. Now, what is the issue with the MOSFET when we are using it as a current source? So, what is the issue? That we will see. So, there will be a current I. If the MOS is acting in a saturation region, there will be a current I. So, what that current I would be? That would be mu n Cux W by 2L VGS. What is VGS? That is VB minus VT whole square. How will you make this VB? If you have only one supply, if you have only VDD supply, how will you make this VB? By potential divider, right? By potential divider, you will be making this VB. This is R1, this is R2, and this will be your VB. So VB would be R2 upon R2 plus R1 into VDD. So this will be your VB. So basically your I would have been mu n Cux W by 2L R2 upon R2 plus R1 into VDD minus VT whole square. What do you see here? Now this Vt is depending on temperature dependent. This Vt threshold voltage, this depends on temperature. This mu n, this is also temperature dependent. This Vb voltage, bias voltage, this is supply dependent. Supply dependent. This was temperature dependent. Right? This is also temperature dependent. So what do you observe here? You observe that this Vt, mu and Vdd, this is supply dependent. So all these are temperature dependent. So this I is not constant. With respect to temperature, with respect to change in the supply, it can change. The thing is, in a chip, let's assume you design a chip and there is a VDD supply. So this supply is also not constant. Let's assume if my supply is 1 volt, sometimes it can change to 1.1 volt and sometimes it can change to 0.9 volt. This you will learn when you go into industry. When you see a chip, the supply can change. So this current will not be constant. So here what we get to know is that this I is not constant. So that is the issue. When you use MOSFET as a current source, this I is not constant. So this is the conclusion. So we actually need a constant current source. And for making that constant current source, we use a circuit that is known as band gap circuit. So for making a current source which is independent of supply and temperature variation, we need to use band gap circuit. Now this band gap circuit is out of the scope of this course. Out of the scope of this course. That means in the GATE exam, it will never be asked. Band gap circuit is not useful for your GATE examination. It is not mentioned in the syllabus. Even in the interview, they do not ask it. If you are someone who is doing M.tech and you have mentioned some project using band gap circuit in your CV, then only they can ask you question on band gap. Otherwise, they are not going to ask you question on band gap reference circuit. So if you have a project mentioned, then you can expect some question. Talking about the placement course, in the end I will teach you band gap reference circuit. But for the GATE aspirants, I am not going to teach band gap reference circuit, band gap circuit. Okay. So you just need to know that by using a band gap circuit, we can get a constant current source which is independent of supply variation and the temperature variation. And that current source is known as golden current source. Golden current source. That is constant current source, basically. Constant current source. So we get a constant current source from this BGR circuit, from band gap reference circuit, from band gap circuit. So we get a constant current source. Now you have that current source with you. Now you have a constant current source with you. Now using that current source, you have a constant current source. You have a golden current source. I golden, or sometimes we call it I reference. You have that reference current source. Now using that current source, you need to make more current sources. This is your target. And for that we use current mirror circuit. You already have a current source. By using that current source, you need to make more current sources, which is identical to this IREF or this I golden. So from band gap circuit, you will make a constant current source, and by using that current source, you will make copy of those current sources that will be identical to this IREF. So for that we use current mirror circuit. So with the help of golden current source, we will generate other current sources which are identical to the golden current source or reference current source. So basically, you will already have a golden current source. This is the golden current source you are having. By using this current source in a circuit, this is a circuit. This is a particular circuit. This is a particular circuit. By using this current source, you will make copy of other current sources. You will make copy of the current sources. I copy 1, I copy 2, and this, let's call this as I ref. So this I copy 1 will be proportional to I ref. So if I ref is temperature independent, if I ref doesn't change with respect to temperature variation or supply variation, then this I copy will also not change. If this I copy 2 will also not change because this is also proportional to IREF. So for that we need to use current mirror circuit, but we directly will not use current mirror circuit. What we need to do, we have a golden current source, okay, and from that we need to generate an output current that should be independent of the supply and everything. You have a golden current source. With the help of that, you need to generate a I copy 1 and I copy 2, and that should be independent of supply variation or temperature variation. So we will try making the circuit. First, what we are going to do, we are going to use a resistor. So what I am going to do, I have a golden current source, or I have a reference current source. I will use a resistor now. What I will do, I will use a resistor R. I am calling this reference current source as I naught. Okay. So I am going to use a resistance R. Now this current is flowing through the resistance R. So what voltage drop it will give here? I naught into R. Now this I naught into R voltage drop will be fed to the MOSFET. Now this voltage drop is fed to the MOSFET, and from there we are generating some current. There will be some other particular circuitry here. Let's not make the circuitry, and we will make sure that this MOS is working in saturation region. MOS in saturation region. Let's call this node as V naught. So adjust V naught such that MOS is working in saturation. So till now what we have studied, we have already generated a constant current source. We are passing it through a resistance R. With the help of this voltage drop we are giving it to a MOS, and now this voltage drop that is here, that is I naught R. Now this voltage drop will generate some current that we can call I copy. So let's check out what is the equation of I copy. What will be the equation of I copy? That would be mu n cox W by 12. What is your VGS? VGS is I naught R minus VT. Now this current is not depending on the supply. This is your VDD. So this current I copy. This doesn't depend on supply. So if there is variation in supply, still the current will be constant. If there is some variation in the supply, still the current will be constant. Why so? Because this current is not depending on the supply, but this current is depending on mu n and Vt. Both are temperature dependent. Both are temperature dependent. So that is the issue here. We tried to make a current source, we tried to make a copy of this current source which should be independent of the temperature variation. But this is not the independent of the temperature variation, it is depending on the temperature. So this is not a good idea. So what we will do now? We will use diode connected transistor. What we will use? Diode connected transistor. Have you studied about it? Yes. In the common source amplifier, I told you about diode connected transistor. So how does the diode connected transistor look like? This is a diode connected transistor. Okay. So I will make it properly. So what I will do? I will pass the current. Which I was having, which is I naught. So I will pass this current from a diode connected transistor. Passing the current from a diode connected transistor, that will generate some voltage V. Are you getting this point? And then this voltage V, I will be giving it to some MOS. This voltage V will be fed to some MOS. This I am going to do. So let's find out what is that voltage V. So what is this I naught? This I naught will be flowing here because there will be no current coming here, right? There will be no current coming in this path, and there will be no current here as well. So there is zero current here. So let's find out the voltage V. So what that voltage V would be. So what is I naught? I naught is equal to mu n cox W by 2L. VGS, what is VGS? VGS is V minus VT whole square. So what is your V? V is under root 12 by mu n cux w, 12 by mu n cux w into I naught plus Vt. Well and good. 12 I naught plus Vt. This is V. Now this V is fed to some other MOS that we are going to connect here. This V is fed to some other MOS. There will be some particular circuitry there. Let's not talk about it. So now here there will be I copy, and we have to adjust V naught. By using some circuitry here, we will adjust V naught such that let's call this one as M1. Okay, this one as M2. So this W by L would be of M1. We will replace it. This W by L would be of M1. This W by L would be M2. So here the W by L is W by L of M1, and here the W by L is W by L of M2. Right? So I guess I should change those equations because I need to write W by L of M1. So what will be your I naught? I naught would be mu n cux W by L of M1 divided by 2 VGS minus VT whole square. So what will be V? V will be 2 I naught upon mu n cux W by L of M1 under root plus Vt. This is the equation 1, and this voltage is fed to this M2, and you have adjusted V naught such that M2 is working in saturation region. Now if M2 is working in saturation region, then what will be the equation of I copy? I copy would be mu n cux W by L of M2 by 2 into V minus Vt whole square. What is V? This is V. V minus Vt whole square. So that would be equals to mu n cux by 2 W by L of M2. What is V? V is this root 2 I naught mu n cux W by L, root 2 I naught mu n cux W by L of M1 plus Vt minus Vt whole square, right? This was your V. I replaced V here, nothing else. Vt will be get cancelled, and this root will be cancelled by square. So what you are getting? This mu n cux will be cancelled. 2 and 2 will be cancelled. So what do you get? So this I copy would be simply equals to W by L of M2 divided by W by L of M1 into I naught. That's it. This is your I copy. So here the current is independent of the supply variation, also the temperature variation, because the current is neither depending on mu n, neither it is depending on Vt, nor it is depending on VDD. Are you getting this point? Neither on supply, neither on temperature. So this I is independent of supply and temperature variation. So no matter if supply changes, variation. If supply changes or temperature changes, the current will be constant, and that will be proportional to I naught. So this was our target, to produce a current which is proportional to the golden current source, and that we have done using two MOS transistor. One was diode connected load, and the other was you made sure that M2 is working in saturation region. So this particular configuration is known as current mirror circuit. Okay, so let's write down the conclusion of the current mirror circuit, or better I should write the conclusion here only. So we are doing the alternative analysis of current mirror circuit. So let's just assume this is V naught. Now this is current mirror circuit only when both M1 and M2 are in saturation region. M1 is certainly in saturation region. Why so? Because drain and gate are shorted. If drain and gate are shorted, that means it is certainly working in saturation region. We have to make sure that M2 is also working in saturation region. M2 is also working in saturation region. How you will make sure? By adjusting VDD and R. By adjusting VDD and R, you can make sure that it is working in saturation region. Because if you adjust VDD and R, V0 will be adjusted. So you have to keep V0 such that your M2 is working in saturation region. So what is the condition? What is the condition for current mirror? Both M1 and M2 are working in saturation region. Both M1 and M2 are in saturation. This is the major condition, that both should be working in saturation region. If one of them is in linear, then the situation will be different. Well and good. So write down the I naught equation. That would be mu n Cux W by L of M1 VGS minus VT. Let's assume this is V. Both have same VGS. This has VGS equals to V. Here also VGS equals to V. So VGS of M1 should be equals to VGS of M2. That is equals to V. Say yes or no. Right? Mu n Cux W by L VGS minus VT whole square. What will be your I out? This is your I naught. What will be your I out? This is the I out. What that will be? That will also be mu n Cux W by L of M2. VGS, what is VGS? V minus VT whole square. Let's call this as equation 1, this as equation 2. So equation 2 divided by equation 1. What do you get? Equation 2 divided by equation 1. So I out by I naught. That would be equals to W by L of M2 divided by W by L of M1. So from here, what do you get to know? That your I naught is equals to W by L of M2 divided by W by L of M1 into I naught. That's it. So the current that is copied, that depends on that W by L ratio only. That's it. Let's see a simple example, very simple example we can see. I will add up a page. Very straightforward, very simple example. I will just frame it here only. Let's call this as VDD. VDD is, I am assuming it to be 5 volt. VDD is 5 volt. This resistance R is 2 ohm. Then there is this diode connected transistor. Then there is this another transistor. Okay, there will be some circuitry ahead, and this is your, forget about it, no V not nothing. W by L of this, if this has W by L, this has 2 into W by L, and this is your I out. This potential is given, that is equals to 1 volt. And also what is given? It is given that both transistors are working in saturation region. In saturation region. This is given. Find I out. Find I out. This is the question. Find I out. So what will be I out? I out would be W by L of transistor itself. Okay, forget that. First find the current here. If this is 1 volt, if this is 0, this will be 1 volt. So this will also be 1 volt. So what is the current here? That is 4 ampere. Sorry, 4 by 2, 2 ampere. Now is there any current here? No. 0 ampere current here, 0 ampere current here, so there will be 0 ampere current here. So the complete 2 ampere current is flowing through this transistor. So this is the 2 ampere current that is flowing. So in the transistor, if 2 ampere current is there, what will be the current here? That would be 2 into W by L of this transistor divided by W by L into 2 ampere. So I out would be 4 ampere. That's it. You just need to go by the W by L ratio. 2 ampere current is flowing. If the W by L is doubled, current will be doubled. If 2 ampere current is there, if W by L is tripled, then the current will be tripled. If W by L is half, the current will be half. 2 ampere, half, 1 ampere. 2 ampere double, 4 ampere. 2 ampere triple, 6 ampere. Are you getting this point? That's it. 2 ampere current is here, it will be doubled. But make sure both the transistors are working in saturation region. That is the most important point. Both should be working in saturation region. That's it. That was the complete analysis. Let's move on to our next topic, that is current mirror circuit but using PMOS. Same, that's it. This is the current mirror circuit using PMOS. So here, this is the current that is flowing through M1. I naught current is flowing through M1. And the what will be I out? So I out would be equals to W by L of M2 divided by W by L of M1 into I naught. So this will be your I out. That's it. Are you getting this point? So this is the concept of current mirror circuit. Well and good. Let's solve a question. So both transistors are perfectly matched. This is given. Both transistors are perfectly matched. What do you mean by perfectly matched? That means they are having same W by L. Same W by L. W by L is 10 for both of them. You need to find the value of R to get 100 microampere output current. So it is given that output current is 100 microampere. If both are having the same W by L, that means what is the current here? Tell me. Look, both transistors are perfectly matched. Okay, it should be written that V naught is adjusted such that, okay, it is not given. Okay, what is the lowest possible value of V naught? This is what they are saying. What is the lowest possible value of V naught such that this transistor M2 is working in saturation region? The question is incomplete. I should have such that M2 is working in saturation region. So M2 is working in saturation region. This is working in saturation region. This is also working in saturation region. That means both are in current mirror and both are matched. That means if 100 microampere current is there, this will also have 100 microampere current. So in the transistor M1, I know there is 100 microampere current. Well and good. There is 100 microampere current. What else is given? Vt value is given. Mu n so x W by L value is given. So mu n so x W by L value I am having. I don't have the VGS value. So first I will find the VGS value. This potential V. First I will find the potential of V. So what I can see here is that at 100 microampere current is equals to mu n Cx is 200 micro into W by L is 10, right? W by L is 10. VGS by 2. What is VGS? VGS is V minus Vt is 0.7 whole square. So you can solve this equation. It will be V minus 0.7, that is equals to under root 10. Under root 10 is nearly 0.3, 0.314 near around that. So V will be nearly 1 volt. So V value you are getting is nearly 1 volt. So this V we got, that is 1 volt. This we can show in the next page. So this potential came out to be 1 volt. And the same potential will be going here, right? So what do you understand by that? 3 minus 1 by R is equals to 100 microampere. Say yes or no? Because there is 0 ampere current here, 0 ampere current here, so 0 ampere current will be coming from here. So 3 minus 1, that means potential drop is 2. 2 by R is equals to 100 microampere. So what is the value of R? That is 20 kilo ohm. The value of R is 20 kilo ohm. That is our first answer. Well and good. Very good. Okay. Now they are asking what should be the minimum value of V naught such that M2 is working in saturation region. So what should be the minimum value of V naught for saturation region? VDS should be equals to VGS minus VT. What is VDS? That is V0. What is VGS? That is 1. Minus VT is 0.7. So V0 value should be 0.3. So what is the answer? V0 is 0.3 volt. What did you understand here? You understood that you have to make this, if you are making this circuit, you have to adjust V0 such that it is 0.3 volts so that it is working in saturation region. Now both are in saturation region, both have the same VGS, that means it is in current mirror. So 100 microampere current here, 100 microampere current here. By that you can get to know the value of R as well. So this was a very easy question. You could have solved it very easily, right? V value we find out, from that we could find out the value of R and V0. Well and good. Okay, let's move on to our next concept. We will be building multiple current sources using current mirror. Multiple current sources. Here what did we do? We found out only one current source. I out. Only one current source we have made. We can make multiple current sources. How we will do it? So this is our VDD. We already have a golden current source, that is I0. Now from this golden current source, I got to know there will be some circuitry here. Forget about that. This was M1, this was M2. So here what was my I copy 1? This was the current that I was getting, which was I copy 1. So my I copy 1 was, better I should write what here. I copy 1 was proportional to the W by L ratios. W by L ratio of M2 divided by W by L ratio of M1 into I0. This was the I copy 1. Now what I can do, I will make one more MOS here. Similar thing I am doing. Okay, this is M3. I have to feed some voltage here, right? I have to feed some voltage here. That voltage will be this potential only. Simply this potential. I am feeding this potential only. Similarly, I can add more transistors. This will be my I copy 2. Similarly, I can add more transistor. Let's assume I add M3. So the same voltage I am applying it here as well. So I am giving the same bias to this one as well. Bias means DC voltage. I am giving the same bias to this one as well. So if this is having V potential, if VGS value is V here, then this is also having VGS value. Now this is 0, this is V. So V is traveling here and V will reach here. So basically, again the potential is V. This is 0, this is V. So V is traveling, will reach here. So this is again V. So all are having V potential, and we make sure that all the transistors are working in saturation region. All transistors are in sat. We have to make sure this, that all transistors are working in saturation region. So all are working in saturation region, all are having the same potential. So basically the current will be copied, right? This will be I copy 3. So the current will be proportional to the W by L ratio. That's it. So I copy 2 would be what? Better write it here. What will be your I copy 2? That would be, if this is M2, this should be M3 and this should be M4. So W by L of M3 divided by W by L of M1 into I0. This will be your I copy 2. And what about I copy 3? I copy 3 also you can write W by L of M4 divided by W by L of M1 into I0. Say yes or no, right? So this is the circuit. Now this circuit sometimes is shown in a different manner. So I will add a page. So here I will write other way of showing the same circuit. Other way of showing the same circuit. Same circuit. So sometimes in the questions, this particular circuit that is shown here, this particular circuit, it's shown something like this. Let's copy this circuit first. So these supplies will be gone. They will not make the connection like this. Instead, what they will do, they will make a line like this, like this. They will make a line like this. Okay. Let's make a clearer structure. They will make a line like this. Here also they will make a line like this. What do they mean by that? That this node is connected to this node and this node is connected to this node. So all these nodes are connected. So the same circuit is shown like this. Are you getting this point? This is M2, this is M3. So in the examination, if you see these kind of circuit, what will you understand? You will understand this, that this potential is connected here, again this potential is connected here. So all the potential are common. That means this V potential is here as well. This V potential is here as well. This V potential is here as well. It doesn't mean that they connected a wire like this. They connected a wire like this. In the previous question that we have shown, they are connecting the wire like this, but shown like this. Okay, this will be your I copy 1. And this will be your I copy 2. This will be your I copy 2. So in the same way it is shown, and these equation will be the same, nothing different will be there. Are you getting this point? So this is the same way of showing the other way of showing the same circuit, right? Let's see what we are going to check. So this is a question which we will be solving now. Okay, so let's solve this question. Actually someone came in the room, so I had to stop the video. So yeah, let's solve this question now. You have to make a common source amplifier using NMOS. So common source amplifier that will be made using NMOS with a 100 microampere current source in load. Okay, till now this is the question. 100 microampere current source in load. 100 microampere current source in load. This is the common source amplifier. Load will be at output. So this is the 100 microampere current source. Now this 100 microampere current source, from where you will be getting this? They are saying that you have a reference current source of 200 microampere. So from 200 microampere, you need to make 100 microampere. This is your task. Your task is to make this current source. How will you make from this 200 microampere current source? So that we will do. Okay. And what else they are giving? They are saying that you have only one supply VDD. You have only one supply. Here I cannot apply my input like this. That this is my small signal input Vin plus VGG. I cannot apply like this. Why so? Because I don't have VGG. I have only one supply. So if there is only one supply, how do you bias it? We have already seen it, right, in MOSFET amplifier. This is how we bias it. You have only one supply, that is VDD, R2, R1, and here I will apply my small signal input, that is my Vin. What else they are saying? Your small signal input Vs has an internal resistance Rs. So this my small signal input is something like this. It is having Vs and it is having Rs. So this is how I will apply my small signal input. Are you getting this point? This is the coupling capacitor. So when you do the DC analysis, only this will be in action. And when you do the AC analysis, this will come in action and there will be no use of this R1 and R2. Are you getting this point? Well and good. And now after designing the complete circuit, you have to find the small signal voltage gain. Now this is not the final design. Why it is not the final design? Because you have to design this 100 microampere current source. So how will you design that? Using current mirror circuit. Are you getting this point? What did they ask you to design? A common source amplifier with a 100 microampere current source in load. That's it. Then they said that you have only VDD. Okay, only VDD I am having. Then I have to bias it. How will I bias it? By using potential divider. R2 by R1. Resistor divider or potential divider using R2 and R1. I have to apply small signal input as well. Small signal input is having RS resistance. So VS, RS, then there is coupling capacitor. So this is my design. This is not the final design because I have to make this 100 microampere current source as well. So now my next task would be what? What is my next task? That is designing 100 microampere current source from 200 microampere reference current. Now, where is your current source going? Your current source is going from VDD to some node. Say yes or no. It is going from VDD to some node. So if it is going from VDD to some node, so what we will have to use? Top to some node, we will use PMOS. You cannot use NMOS. We will use PMOS because it is going from VDD to some node. Top to some node. Top P for PMOS. So we are designing a 100 microampere current source from 200 microampere reference current. So you are having a 200 microampere reference current. 200 microampere reference current. This is what you are having. You will pass it through a PMOS, which is a diode connected transistor. So you are passing it through a PMOS. You have only one supply, that is VDD. And then one more PMOS will be there. You have only one supply. Source should be at higher potential. And here there will be some circuitry that we have already seen. So this is the 200 microampere current source which is flowing in this MOS as well. Let's just call this has W by L ratio. If this has some W by L ratio, what should be the W by L ratio of this transistor? It should be half of this. Are you agreeing to my point? Because if this is having 200 microampere current, and then if this is having half of W by L, then it will be having 100 microampere current. Are you understanding this point or not? So what was the question? You have to, these specs are given, you have to design the circuit. We started designing the circuit. We made this much of circuit, then we got to know we have to design a 100 microampere current source from 200 microampere reference current. This is the 200 microampere reference current we are having. We also got to know we have to design the current source such that it is going from supply to some node, supply to node, top to node, top P. That means we have to use PMOS. So we are using PMOS, 200 microampere current that is flowing through W by L. Then half of W by L will have 100 microampere current. So this is the current source that we have made. So this was our next task. So what will be your final design? Final design. So this is the final design I am having. This is 200 microampere current source. Here both are having the same VSG. Both are having the same VSG. And yeah, I have to write one more thing. Making sure that this transistor is working in fact. You have to make sure that this transistor is working in saturation region. Okay. This is, let's call this transistor as M3, this transistor as M2. Now this 100 microampere current source is fed to a common source amplifier. This is the V naught we were having. Also, by using this VDD supply and a potential divider, I was getting my DC bias. This was R1, this was R2. This was the DC bias I was getting, and then I had my small signal source here. So this is my final design. I am done with my final design. I used only one VDD. I used only one supply. I had the resistance R1, R2. I got the bias from there. These are the transistor I am having. Let's call this transistor M1. I will adjust VDD R1, R2 such that all transistors are working in saturation. All transistors should be working in saturation. Why these two should be working in saturation? Because this is current mirror. And why this should be working in saturation region? Because you are using it as an amplifier. So all transistors are working in saturation region. This is having 200 microampere current, and what is the other relation? W by L of 3 is 2 times of W by L of 2, right? This is doubled, this is doubled, M3 is doubled, so this is half, right? So W by L of 2 is half of W by L of 3. So here there is 200 microampere current, so this will be having 100 microampere current. So this is our final design. Now what did they ask? This is not the final answer. They asked to, after designing the circuit, find the small signal voltage gain. Now you have to find the small signal voltage gain. So how you will find it? This is a very, very important concept. Watch it carefully. So I will find the small signal voltage gain now. So for finding the small signal voltage gain, what do we do? This supply will be shorted. So this will be shorted. What will happen to this current source? This will be open circuited. This current source will be open circuited. This circuit will be reduced something like this. Say yes or no. Are you agreeing to my point? This is M3. So from source to drain, you are having a R0 resistance. This is M3, so it will be having a R0 3 resistance. Say yes or no. R0 3 resistance, right? Forget about this 100 microampere. This VDD will also be shorted. This will also be shorted. This is having a R0 2 resistance. What about this? This VDD will be gone and R1, R2 will come in parallel. So better we make it like this. What will happen? This is Vs, this is Rs. R1 and R2 will come in parallel. R1 parallel R2 will be connected like this. Say yes or no. Are you agreeing to my point? What will happen to this circuitry? This is the task. What will happen to this much of circuitry? Because one thing I know, that from V0 to ground, from this V0 to ground, I see R01. From V0 to ground, I see R01. From V0 to ground, I see this MOS, and from V0 to ground, I see this much of circuitry. What will happen to this circuitry? Tell me. Let's assume there is V potential here. There is V potential here. So what I can say? From V to ground, I see R03. And from V to ground, I see 1 by GM3. Say yes or no. I told you, if there is this arrow, that means there is 1 by GM. Or how you can say, if this is V potential, V potential, then how much current is there in this MOS? GMV. GMV. Will there be any current? No. Will there be any current? No. So will there be any current? No. So this V potential is, this M3 is having GMV current. So this V potential will be coming here as well, right? So from V potential, what do you see? From V potential, there is R03 current. Sorry, from V potential, there is V by R03 current, and from this V potential, there is GM3V current. This is GM3 V current. So what is the impedance you can say? R03 parallel with 1 by GM3. Say yes or no. Let me show you the circuit once again. What is the circuit? This is the circuit. These are shorted. This is also shorted. Here there is R0. And this is potential V. This potential V is carrying here as well. If this is V potential, that means here there is GMV current. Forget about this R0. Let's call it R0. You need to find the impedance from here. You need to find the impedance from here. So let's just assume if this is V potential, then what is the current here? That is I. So if this is V potential, this is the current I. So this I current would be equal to, there is no current here, there is no current here. Just a second. Yeah, so what I was saying, so from V to ground you see GMV current, from V to here you see V by R02 current, right? So V by R02 plus GMV R02 or whatever it is R0, V by R0 plus GMV is equal to I. So what is the resistance you see? 1 by GM parallel with R0. Or you can directly say from V to ground I see 1 by GM, from V to ground I see R03. So this much of circuitry, this much of circuitry will be replaced by simple resistance. This much of circuitry here will be replaced by simple resistance. From V to ground, what do you see? 1 by GM3 parallel with R03. Now, this is the circuit. 1 by GM parallel with R03. Now, this potential is being fed here. Now, this is the same, right? You are checking from V0. You are checking from the point of view of V0. Because your final target is from V0 to ground, what do you see? This is your final target. Okay. Now, this much of circuitry is replaced with a single resistance, that is 1 by GM3 parallel with R03. Now, how much current is this will have? Because here there is 0 ampere current. So, how much current this resistance will have? 0 ampere current only. This will also have 0 ampere current. This is ground, that means if, and this resistance is having 0 ampere current. So, that means this voltage will be 0 volt. Are you agreeing to this? 0 ampere current is flowing. So, this potential will also be 0 volt. So, basically, this potential, this will be replaced with ground only. Yes or no? Here there is 0 ampere current, right? Also, this is also 0 ampere current. So, this will be replaced with ground. Here VSG is gone. If VSG is gone, that means there is 0 ampere current. So, basically, this much of complete circuit is replaced with single resistance R02. Say yes or no. Did you understand? This configuration was replaced with resistance 1 by GM3 parallel with R03. Then I got to know that this became grounded because there was 0 ampere current here, so this node would become grounded. If this is grounded, that means VSG is gone. If VSG is gone, that means MOS is having 0 ampere current. If MOS is having 0 ampere current, so from V0 to ground I see only R02. Say yes or no. So from V0 to ground I see R02, from V0 to ground I see here R01. Right? So what is the equivalent? Now what is the final equivalent? This is my VS, RS, R1 parallel R2. This is RS, this is VS. This is V0. So from V0 to ground, I see R01. From V0 to ground, I see R02. Now, whatever the potential that you get here into GM1 will be the current flowing. So then you can write down the gain. We have seen it in common source amplifier. So no worries about that. This was our one. This was our second. This was the final circuitry. So I hope you are understanding it. What will be the gain? Now I will directly write down the gain. You should be comfortable with this. What will be the gain? V0 by Vs. That would be GM1 into R minus sign certainly will be there because this is common source amplifier. R01, R02 into R1 parallel R2 upon Rs plus R1 parallel R2. Say yes or no. This is V naught by Vs. Are you agreeing to my point? This gain you can write. First write down the potential here, then the current here would be GMV. GM1V. The same current is flowing through R0 or this final output impedance. That current would be GMV. That current is flowing through V0. So what will be your V0? V0 would be GM1 into R01 parallel with R02 and minus sign. And what is the value of V? Value of V is R1 parallel R2 upon R1 parallel R2 plus Rs. So from there you could get this final answer V0 by Vs, that is this. So this was the first method from where you could find the small signal voltage gain. Now what is the other method? Here I know that this is a 200 microampere current source and this current source is copied into 100 microampere, right? So I can replace this much of circuitry with a simple current source, but that has some output impedance. This much of circuitry can be replaced with a simple current source that has the output impedance of M2. The output impedance of this side will not matter. Why? Because whatever the impedance we are having here, that will be going towards 0 only. Whatever the impedance we are having here, that is going towards 0 only. So only the impedance of this side is mattering. Impedance of this side is matters. Only impedance of this side matters. That's it. So the side which is connected to the M1 MOSFET, only the impedance of that side is mattering. So whatever the current that is being pushed into M1, whatever the current that is being pushed into M1, only the impedance of that side matters. That's it. So what is our method 2 now? Method 2. So simply we have a 100 microampere current source here. Now how much output impedance this 100 microampere current source is having? From this particular node you will see, that is R02, right? So you will make that this is the 100 microampere current source you are having, which is having a resistance of R02. And then you are having a common source amplifier. This is Vs, this is Rs, this is V0, and this is grounded. And if you are doing the small signal analysis, then this 100 microampere current source will also be gone. Why it will be gone? Because this is a DC current source. What do you see? From V0 to ground, you only see R0 2 resistance, right? And from here you see R0 1 resistance. So simply your circuit is replaced with, from V0 to ground, R1 parallel with R0 2, right? So here I will just make the circuit once again. Here I will make the 100 microampere current source so that students will be comfortable. This is VDD and this R0 2 is connected like this. Then if you do the small signal analysis, this will be gone. And here we are having R1 parallel R2. Or better I should make, here I am making the complete circuit only, not just the small signal. This is R1, this is R2, this is VDD, this is RS, this is V, this is Vs, this is capacitor C. So what will be the final circuit after the small signal analysis? This would be Rs, this would be R1 parallel R2, and here you are having this MOS, and from V0 to ground you are having R0 1 parallel with R0 2, and this is your Vs. That's it. This was your M1. So this is the small signal analysis. Did you get to know? So for gate aspirant, what will be the question? For the gate aspirant, this circuit will be given. In the examination, they will not ask you to design a circuit. But if you learn to design a circuit, it will be very helpful for you. Because just by seeing the circuit, you will get to know, okay, they have designed it in a way that 100 microampere current is acting as a load for common source amplifier. If I had directly given this circuit to you, okay, and I had asked you to find the small signal voltage gain, then you wouldn't be learning anything. You would be only learning how to solve a particular problem. But what we are doing in the complete course, first we are designing something and then we are learning how to solve it. Are you getting this point? This is my objective of teaching this course. First we design, and once you see the question, you should be knowing what they actually want to ask. So if this question was in front of you and they ask you the small signal gain, what you would understand? That they are using a 100 microampere current source as a load. Now this 100 microampere current source will have the output impedance similar to what M2 is having. So from here, what is the output impedance do you see? That is R02. So directly you will make R02. Nothing you will see. You will not even see here because the current is copied here. That's it. So you will make R02, then you will make this M1 and directly you will write down the final gain. So this was the objective. That's why we are spending so much of time, so that in the examination you have to spend the minimum time. And toughest of toughest question you will be able to solve. Say yes or no. Let's move on to our next question. Next question you will be solving it on your own. So this is the next question. You have to design a common drain amplifier. Common drain amplifier will be made using NMOS. Design a common drain amplifier which will be made using NMOS with the 100 microampere current source in load. So you have to design a common drain amplifier. They are not talking about the supply, so we have different supplies now. So common drain amplifier using NMOS. This is the common drain. In common drain, you apply the input here, you get the output here. Apply the input at gate, get the output as a source. 100 microampere current source in load. In load, you are using 100 microampere current source. This 100 microampere current source, you have a reference current source of 200 microampere. From 200 microampere, you need to make 100 microampere current source. But what is the condition? That all the transistors are having the same W by L ratios. This is the condition now. Here, what did you do? That sir, here I am having W by L ratio of W by L, and here my W by L ratio is half of the previous one. But now they have said that all the transistors are having the same W by L ratio. So what you will do now? This is the question. Think about it and tell me. Use your complete brain. Think about it. If you are able to think, then it's very good. If you are not able to think, no worries. Even I was not able to think about it in the first chance. Okay. So no worries if you are not able to think. If you are able to think, that is very good. So what this Vin would be, let's first write it. It will be small signal Vin plus VGG. But they are not talking about supply and anything now. Here I talked about supply and everything. So here I have eradicated all those things. So now our task is to design a 100 microampere current source from 200 microampere golden source, but W by L ratio is same. So what you will do? So my task is now designing 100 microampere current source. How will you design it? You have a 200 microampere current source. One thing I know, that this current will be copied. One thing I know, the current will be copied, right? But the current that is going to be copied, that has to be 100 microampere because W by L ratio is same. What is the copied current? Copied current is W by L of someone divided by W by L of the other one into the current. Now W by L is same. So copied current will be the same as whatever the current that you are having. But the current that you are having is 200 microampere. So you need to get 100 microampere out of it. Say yes or no. How you can get 100 microampere from 200 microampere current? If there is I current flowing, I pass it through two equal resistance. This is resistance R, this is resistance R, this is I current. What will be the current in this one? I by 2. What will be the current in this one? I by 2. The same thing we are going to do here. 200 microampere current you are having. I am going to, okay. Now secondly, what you will use for making a current source now? NMOS or PMOS? For making a current source, what you are going to use? NMOS or PMOS? We are going to use NMOS. Why so? Because we are going from some node to ground, node N, node to ground. That means I am going to use NMOS. Okay, better, I will make a better circuit. Basically, this 200 microampere current should be divided into two parts. 200 microampere current should be divided into two parts, and then that current will be copied here. This current will be copied here. And here there will be the MOSFET amplifier. Here that will be the circuit. This current will be copied. टेढ़ा हो गया भाई. You have to divide the current. How will you divide the current? This should be looking here like this. This should be diode connected as well. Say diode connected, and the same kind of transistor I can add here. That's it. This is your VDD. VDD 200 microampere current is coming. Now that current will be divided into two transistors. Both are having the same W by L, so both will have the same current, 100 micro. This will also have the 100 microampere current. Now this current, this is having V potential. If this is having 100 microampere current, this is having V potential. That means this will also have V potential. Now this same V potential will be fed to this. All are having the same V potential. All are in the saturation region. That means all will have the same current. That this will also have the same 100 microampere current. Say yes or no. Did you understand this question or not? You had 200 microampere. You need to get 100 microampere current out of it. You need to divide that current. I divided that current into two diode connected MOS. Both are in saturation region. Both are in saturation region. Both have the same W by L ratio. That means both will have the same current. So 200 will be divided into two parts. 100 100. Say yes or no. Right? 100 100. Both current are divided. If 100 microampere current is flowing, that means there will be a voltage developed V across them. Both of them will have the same voltage. Why both of them will have the same voltage? Because both are having the same current. That's why both of them will have the same voltage. Or better, I should short circuit their voltages. Or it is already shorted actually. If this is 0, this is V, then this will be V only. Both have the same voltage already. So both have same VGS, both have same W by L, both have same VT, everything is same. That means both will have the same current. So 200 microampere current will be divided into two parts. That will be 100 microampere and 100 microampere. Are you getting this point? So both are having 100 microampere current. Because of this 100 microampere current, some voltage is developed. That is V. The same voltage is fed to the other transistor. Now I am making sure that this transistor is working in saturation region. I will make sure by the supply, I will make sure that this transistor is working in saturation region. So that is having 100 microampere current, which is acting as a load for a common drain amplifier. So what will be my final design? So in my final design, I will copy this circuit only. Array, wow. This current source I have made. So simply I need to use a common drain amplifier here. This was VDD. This is V in. And this is my V out. If this transistor is M, all the transistor that you are having is having same W by L. So all the transistors are identical. all what you are having is NMOS, all transistors are identical. Tell me the small signal voltage gain for this. Write down your final answer and then match it. What is your final answer? GM R naught upon 2 plus GM R naught. If you are getting this answer, just close this video and move to the next video. If you did not get this answer, then watch the solution. If you are getting this answer, forget it. You are great. You have understood everything from this lecture. Just move to the next lecture. If you are not getting it, then watch the video. यही आएगा ना यार कहीं GMR नोट यही आएगा. Okay. What did I tell you? This will have 100 microampere current. This will also have 100 microampere current. What they will act as? They will act as a current source, and their impedance doesn't even matter. Also, what we can do, first let's solve it by the conventional method. What is the conventional method? I need to look the impedance from here. What is the impedance do I see from here? So I need to look that impedance. So if this is voltage V, this will also be voltage V. So here from V2 ground I see 1 by Gm. From V2 ground I see R0. From V2 ground I see R0. From V2 ground I see 1 by Gm. So from V2 ground what do I see? 1 by Gm parallel with R0 parallel with 1 by Gm parallel with R0. Say yes or no? From V2 ground I see 1 by Gm. From V2 ground I see R0. From this V2 ground I see 1 by Gm. From V2 ground I see R0. From V2 ground 1 by Gm. From V2 ground R0. So this much of region will be replaced by 1 by Gm parallel with R0 parallel with 1 by Gm parallel with R0. Say yes or no? Let's do the small signal analysis of this. This is the final design. Now we are going to do the small signal analysis. Small signal analysis. All transistors are already working in saturation, so forget about it. This is 200 microampere, which will be gone. From V to ground 1 by Gm parallel with R0 parallel with 1 by Gm parallel with R0. So this much of circuitry will be replaced by, from V to ground, you are having 1 by Gm parallel with R0 parallel with 1 by Gm parallel with R0. Whatever the impedance you are having here, does that matter? No, because this is 0 ampere current. If this is 0 ampere current, this will also be 0 ampere current. That means this node will be grounded only. And if this node is grounded, that means VGS is gone. And if VGS is gone, so from V0 to ground, you only see R0 resistance. That's it. Are you getting this point or not? And this is also grounded in small signal analysis. And in place of Vin, I will write small signal Vin. So from V0 to ground, I see R0. From V0 to ground, here also I see R0, because the same current, 0 ampere current is flowing here. The resistance is having 0 volt drop. This is 0. This is 0. This is also 0. So VGS is gone. So complete 0 it is. So from V0 to ground, I see only R0. From V0 to ground, I see only R0. So here, this is my Vin. V0 to ground, I see R0 parallel with R0. That would be R0 by 2. And this is grounded. What will be my gain now? This is 1 by Gm here. This is 1 by Gm. So what will be the gain? V0 by Vin. That would be R0 by 2 upon 1 by Gm plus R0 by 2. So what we will get? Gm R0 upon 2 plus Gm R0 V0 by Vin. This is the final answer. So always remember one thing. No matter how many current mirrors do you use here, only the current mirror will matter which is acting as a load. That's it. Only the current source which is acting as a load, that will matter only. These will not matter, because everything which we are having here, that will be replaced by a single resistance. So this is replaced by a single resistance. and here there is 0 ampere current. So this resistance will also have the 0 ampere current. So here that voltage drop will also be 0. If voltage drop is 0, that means there is no use of this. Now VSG is also gone. If VSG is gone, what does that mean? If VGS or VSG is gone, that means this M will be replaced with open circuited. Whatever the output resistance it is having, that will come into action. So this M was having R02 output impedance. So only R02 output impedance will come in action. Say yes or no. Are you able to understand the complete concept? I hope you are able to understand the complete concept. So this is the current mirror that should be taught in the gate field, but it is not taught in this manner. In the small signal analysis should be taught for this current mirror as well. And I will show you the questions which have been asked in the previous gate examination from the small signal analysis of current mirror. So what is the conclusion that we got to know in current mirror? No matter whatever the circuitry you are having here, the final resistance would matter, that is here. So I will write down a conclusion. What is the conclusion? Let's just assume this is a VDD. From here you are having a current source of some ID. Then there will be a lot of diode connected transistor. There can be a lot of diode connected transistor. One, then more will be there. Two, this is also diode connected. There will be more like that. Then there will be this final one. The voltage from this will be fed to the final transistor here, and above that you will be having some circuitry, some amp you will be having. So what do you see from here? What do you see from here? So from here, from V0, what do I see? From V0, at the above side I will see an amp, and here I will see a current source, whatever the current I will get, a current source, and the output impedance of this. That's it. What is the output impedance of M? So R0 of, let's call this M dash. So R0 of this M dash. That's it. This is the conclusion. Are you getting this point? No matter whatever you are having, all will be replaced with a single resistance. And if this is replaced with a single resistance, then 0 ampere current would make the potential here 0. Then VGS will be gone, and if VGS is gone, then only one resistance I see. That is it. I hope you have understood the concept of current mirror. In the next video, we will see very interesting question on current mirror circuit and cascode amplifier. So next will be an assignment which you will be solving. Okay, so that will be assignment 9, I guess, or 10, I don't know. I will check it. Assignment 9 as far as I remember. So next we will see assignment 9. Okay, thank you.